Today, I shall discuss the optimum velocity ratio for reaction turbine and maximum efficiency. Let's start. Optimum velocity ratio of reaction turbine and maximum efficiency. Optimum velocity ratio and maximum efficiency. Now, what is velocity ratio first? Velocity ratio What is velocity ratio? It is denoted by rho equals to Vb by V1. We have to optimize this value to produce the maximum efficiency. Okay, we have to find the optimum value of rho to produce the maximum efficiency. Let's start. First of all, we have to make the reaction turbine. What is reaction turbine? The reaction turbine What is reaction turbine? Reaction turbine having the fixed blade at the inlet and the moving blade. This is fixed blade and this is moving blade. Okay. Now, inlet velocity of fixed blade considering V0 and outlet, that's the absolute velocity V1, and inlet velocity at the fixed blade at the moving blade, this is V1, VR1 and this is VR2. Why it is relative velocity at the moving blade? Because blade already is rotating. At that time I am supplying the steam to this blade should be relative, because it is already rotating and I am supplying the value of I am supplying the steam to this blade must be relative velocity. So relative velocity have to be considered for the fixed for the moving blade, and for the fixed blade the absolute velocity is considered for this blade. Okay. Now, for this turbine we have to find the energy supply. I want to find the efficiency. So efficiency is the work done by energy supply. So first of all we have to find the energy supply. So energy supply to this turbine per kg is denoted by small e equals to kinetic energy change at the fixed blade and kinetic energy change in the moving blade. So addition of the kinetic energy change in the fixed blade and kinetic energy change in this moving blade, if we add these two, then this is the energy supply. So this is the kinetic energy change at fixed blade plus kinetic energy change at moving blade. This is kinetic energy change in this fixed blade. We can obtain this from these two values is half V1 square minus V0 square plus half, for this case VR2 square minus VR1 square. Okay. Now we know the inlet velocity, considering the inlet velocity at fixed blade of steam is negligible, is 0. So V0 equals to 0. So you can write small e equals to half V1 square plus half VR2 square minus VR1 square. And we have to consider the Parson reaction turbine, this turbine. Otherwise this value of the efficiency may not be maximized. The efficiency should be maximum for Parson reaction turbine. So what is Parson reaction turbine? Considering this turbine is a Parson reaction turbine. So for Parson reaction turbine, theta equals to phi and alpha equals to beta. Let's draw the Parson reaction turbine. This is the Parson reaction turbine. This is alpha and this is phi. This is theta. This is beta. So we know this theta equals to phi and alpha equals to beta. So this triangle ABC, this triangle ABC must be ABD. These two triangles are same. Here triangle ABC must be equal to ABD. Okay. Now as we know, this is V1, VR1, this is VR2 and this is V2. We can write this for this turbine. So we can write V1, VR2 equals to V1 and V2 equals to VR1. Obviously right, because these two triangles are same. And also this alpha equals to or phi equals to alpha. Okay. Now for this triangle we can see that VR2 equals to V1. So as VR2 equals to V1, we can find this small e equals to half V1 square plus half this VR2 equals to V1. So V1 square minus VR1 square. We can write this value is V1 square minus half VR1 square. Okay. Now what is VR1? From this triangle, ABC, we can write VR1 whole square equals to this side and square, this value of this triangle, this side is VR1 square, and this VR1 square, that is AC square, equals to BC square plus AB square minus 2 AB AC cos alpha. So you can write this is V1 square minus this value is VB, this value is VB, so VB square minus 2 V1 VB cos alpha. We can obtain this VR1 square from this equation, triangular equation. Now we can put this value of VR1 square to find the small e equals to V1 square minus half. Put this value V1 square plus VB square minus 2 V1 VB cos alpha. This equals to, you can see that they both having the same values, so we can write half V1 square V1 square minus VB square plus 2 V1 VB cos alpha. Okay. Now find the work done. This is the energy supplied. Now we have to find the work done. Work done. As we know, the ratio of work done by energy supply, that is the efficiency. So we have to find the work done. So work done equals to work done per kg. Now I want to find work done per kg in this form. This value will be VW1 plus VW2 into VB. This value will be VW1, that is VW1, this value is VW1, this value is VW1. So VW1 is V1 cos alpha, plus, how you can find this is VW2. How you can find VW2? That is VR2 cos phi minus VB. Is not it? Now this is V1 cos alpha plus VR2. VR2 means V1 cos alpha cos phi, this phi equals to alpha, so this cos alpha minus VB, and sorry, here this value VB is there, VB, so this value will be also. Now this value will come to V1 cos alpha, because this value having same, minus VB into VB. This equals to 2 V1 VB cos alpha minus VB square. Okay. Now we have to find the efficiency. You can see this efficiency is work done per kg by small e. This value will come, work done per kg 2 V1 VB cos alpha minus VB square, and this value E is half V1 square minus VB square plus 2 V1 VB cos alpha. Okay. Now if we divide both this side by V1 square, if we divide this side by V1 square, this by V1 square, this by V1 square, this by V1 square, this V1 square, we can get, as you know, this 2 is there, so I can write 2 here, and if we divide by V1 square, we can get VB by V1 cos alpha minus VB by V1 square. Here also V1 will be 1 minus VB by V1 square plus 2 VB by V1 cos alpha. This value will come to rho cos alpha minus rho square, because VB by V1 is rho, so I put this value rho, and this will be 1 minus rho square plus 2 rho cos alpha. Now to make this both this side as same, we have to write like that. That is, you can see that minus rho alpha is present here, 2 rho cos alpha, sorry, it having 1, then 2 here, so this will be 2 also. Here this 2 is there, so already there is mistake. Now you can see that both this side having same, only one not present is there, so we can write as same 2. I have taken this 1 plus 2 rho cos alpha minus rho square. As I taken this value 1, so I have to put here 2 again, and you can see that this is 1 minus, for this case, plus 2 rho cos alpha minus rho square. So you can see that both this side having the same values, so I can write this value, that is 2 only remain because both having the same values, minus 2 1 plus 2 rho cos alpha minus rho square. Is not it? Now we have to make the maximum value of sigma. If we want to produce the maximum value of sigma, we have to produce this value is maximum. To produce the maximum value of sigma, we have to produce the maximum value of this total. When this value will be maximum, this value should be minimum. Only this value should be minimum. When these values will be minimum, this should be maximum. When this value will be maximum, this value will be maximum. You can see. Again, to produce this maximum value of sigma, we have to produce this value is maximum. When this value will be maximum, at that time we require to produce this value is minimum. This value will be minimum when this value will be maximum. So if we produce the maximum value of this one, this value will be maximum. So I want to maximize this value is d, differentiate this equation by this one is d rho, that is given 1 plus 2 rho cos alpha minus rho square, and this will be 0. To make this equation maximize, we have to differentiate n equals to 0. So this value will come is 2 cos alpha minus 2 rho, this will be 0, and that's mean this rho equals to cos alpha. What is this? This is the optimum value of the rho. This is optimum value of rho. This rho optimum equals to cos alpha. That's mean if we put this value in case of rho, then maximum efficiency will obtain. Now find the maximum efficiency. Efficiency will be maximum. We know first of all this efficiency value we got, this value is this value, it's not it, this value. So first of all I can write this value is 2 rho cos alpha minus rho square 1 minus rho square plus 2 rho cos alpha. Now put the value of rho, optimum value of rho, to get the maximum efficiency. So maximum efficiency, if we put the rho equals to cos alpha, we got this value 2 rho equals to cos alpha, again cos alpha minus cos square alpha, and 1 minus cos square alpha plus 2 cos alpha cos alpha. You can put this, you can find this value is 2 cos square alpha minus cos square alpha divided by here 1 minus cos square alpha plus 2 cos square alpha. Now this value will come 2 cos square alpha by 1 minus cos square alpha. This is the maximum efficiency. So this is the maximum efficiency for reaction turbine, and this is the optimum value of reaction turbine. Okay.